Our consideration of a sum of two variables gives us almost all we need for sums of many variables, but there is one technical point, and it is as well to take stock of it. It will help also reinforce and settle our ideas of independence, and then we can move on with a general formulation under our belt. So accordingly, let us start with a setting of repeated independent trials, and we are going to think of independent variables with a common density. So let's say x is a chance variable, a generic chance variable, and let's say it's got a mass density function p of x, and let us suppose that x has got an expectation mu and a variance sigma squared. We consider x1, x2, x3, and so forth, a potentially infinite sequence of such coordinate variables, to be independent realizations of variables with the same density as x. In other words, we have a setting of repeated independent trials. Now, in this setting, what is going to be of interest to us is when we form partial sums of the sequence. So the idea here is, instead of looking at a single chance experiment where we add a certain number of variables, we look at them in sequence. We look at an infinite collection of such chance experiments by looking at various partial sums. In our usual notation now, let S1 be just x1. S2 is a sum of the first two coordinate variables, S3 is a sum of the first three coordinate variables, and Sn is a sum of the first n coordinate variables. N, of course, is a generic number, and we're going to start thinking about n as it becomes larger and larger and larger. Now, in this setting, a simple observation smooths our path and allows us to connect a general setting to the setting of the sum of two variables that we have already seen. Accordingly, let's start with S2. We recognize that x1 is just S1, so we can rewrite S2 as S1 plus x2. Similarly, S3 is the sum of x1, x2, and x3, but x1 plus x2 is S2, and therefore S3 is S2 plus x3. And now we see an immediate pattern. So for the nth of these partial sums, Sn is Sn minus 1 plus xn. Let us focus on the last line on the screen. Sn is a sum of Sn minus 1 and xn. A key and beautiful observation may be made at this point, to wit, that Sn minus 1, the sum of the first n minus 1 coordinate variables, is independent of xn. The listener might feel that this seems obvious. After all, Sn minus 1 depends on the first n minus 1 coordinate variables only. And the first n minus 1 coordinate variables, x1 through xn minus 1, are individually, severally, and collectively independent of the nth coordinate variable xn. And certainly that is true. Right? How do we go about verifying this? Well, the pattern follows exactly the procedure we took to verify that x1 through xn were individually independent. And here we go. So to verify independence, we have a variable Sn minus 1 and a variable xn. We're going to ask for the joint probability, the probability of the intersection of two events, that Sn minus 1 takes values in a certain range and xn takes value in another range. So think of A as some subcollection of real values, maybe an interval or a collection of intervals, B as some other interval perhaps, or some other collection of intervals, and we're asking for the joint probability of the event that Sn minus 1 lies in A and xn lies in B. How do we go about doing this? A quick sanity check. What is the underlying sample space? Well, the space we're dealing with, as far as x1 through xn are concerned, is n-dimensional Euclidean space. So we have an n-dimensional Euclidean space. We're going to identify the event of interest in it. What is the event of interest? Well, that portion of the space where the first n-1 coordinates adds up to a number which lies in a region A, and the last coordinate lies in a region B. We simply add up, or in our case now, integrate over that region. So accordingly, the notation is looking a little formidable, but the logic now is impeccable. Right? We are cutting up a region of n-dimensional space described by the following relationships. The first n-1 coordinate variables must add up to a number which lies in a region A, and the last coordinate variable must lie in B. And what are we adding up, integrating? Naturally, the joint density of the n coordinate variables. And here is where independence comes to play a key role. Because the variables are independent, the joint density is a product of the individual densities. But each of the individual densities is described by exactly the same function. They all have the same distribution. They are all governed by the same density, P. And so you have P of x1, which tells you the density of the first coordinate variable at the point x1, multiplying P of x2, the density of the second coordinate variable at the point x2, and so on down. And there you have it. Now, once you've got an integrand which peels off so beautifully into a product of individual pieces, then naturally now we can separate the integrals and do the integration iteratively. And we break it up into two pieces. A segment where we are doing an integral over the first n-1 coordinate variables. Over what region? Well, exactly the region where the sum of those variables lies in A. And then a second integral where we have xn lying in B. Now, observe that the last integral is accumulating the probability over the region B for the nth variable. Or, in a more familiar notation, this stands for the probability that the nth coordinate variable takes values in B. Now, that's nice and simple. What about the big, ugly, multiple integral mess in front? Well, if you look at it carefully, it says, this describes an event involving the first n-1 coordinate variables where their sum lies in A, or in other words, it describes the probability that Sn-1 lies in A, and there you have it. The probability of the intersection of the two events is a product of the two probabilities, and Sn-1 and Xn therefore are independent. With this key observation under our belt, now let's go ahead and see what happens to expectations and variances for the partial sums. So let's build up a story one step at a time, starting at n equal to 1. Well, S1 is x1, so this is trivial. The expectation of S1 is the same as that of x1. It's mu. The variance of S1 is sigma squared. The first non-trivial case is S2. But S2 is S1 plus x2. S1 is independent of x2. Both these variables have got mean or expectation mu, and both of them have got variance sigma squared, and therefore the expectation of S2 by our additivity result is twice mu. The variance of S2 by additivity, because the summands are independent, is twice sigma squared. Oh, and now it's easy to build it up. S3 will add S2 to X3, and if we keep doing this, Sn will add Sn minus 1 to Xn. Again, now we have two independent variables which are being added, and therefore, by the inductive process, it's now clear that the expectation of Sn is n times mu, and the variance of Sn is n times sigma squared. Beautiful. Additivity has managed to wrap up and put in a very compact package both the expectation and the variance of these partial sums. The density of the partial sums is a much more complex affair. No matter. the expectation and the variance leverage additivity, and we've got these beautiful compact expressions. Now, this story is already telling us a little bit more. The expectation of Sn is n times mu, or another way of saying this is the expectation of Sn divided by n is mu. And our experience with the binomial suggests, therefore, that we might anticipate that Sn divided by n concentrates near mu is a good estimate of mu. And indeed it does. And this is going to be the content of the law of large numbers.